In this second part of the ARDL Bounds Test presentation, I'm going to outline the estimation process. And so again, what we're dealing with here is a mix of I0 and I1 time series variables. There's not going to be any I2 involved here. So, and with this mix, that would obviously not allow us uh, to utilize the Johansson's test of co-integration. We're going to have to go with the ARDL Bounds Test in the sense of Pesaran and his co-authors, Shen and Smith, to see if the variables are co-integrated. And so here's a quick sum of the estimation process. In the first hand, we're going to specify the ARDL Bounds Test model. And secondly, now with that model, we're going to determine the optimal log structure to use. And thirdly, most importantly, we're going to perform the bounds test to see if in fact the series are co-integrated, meaning if the series have a long-run relationship. Now, if we find that they are co-integrated, then we can go ahead and boldly specify the error correction model to investigate the long-run dynamics. And in that sense, we're going to first of all run the long-run model and obtain the residuals of that model, which actually is what represents the error correction term. And then with that error correction term in place, we're going to go ahead and estimate the vector error correction model. And additionally, we can also estimate the short-run ARDL model to examine the short-run dynamics of the relationship between the dependents and the regressors. Now, if we find, however, that the series are not co-integrated and that the bounds test analysis didn't amount to a hill of beans, then we would only be going ahead and specifying the short-run ARDL model to examine their short-run dynamics. So that's basically it. And at the end of the journey, we want to make sure that all is well in paradise by performing some essential diagnostics. In my opinion, the two most important would be serial correlation test and test of model stability. But you can also do additional stuff, such as checking to make sure that that there's normality and also that there's no heteroscedasticity. Anyhow, so this is the bounds test specification right here, which consists of two components, the short run component and the long run component. So this is the key contribution right here. The coefficients of the long run terms are phi1 and phi2 in this two variable representation. And so actually this simply includes the lagged values of y and x, the dependent and the explanatory variable respectively. And so we're going to perform a bounds test to see if in fact that we have co-integration in that we reject the null hypothesis that phi1 equal phi2 is 0. If we reject that, then we can say, hey, there's co-integration. And then separately, we're going to also test these short-run coefficients, lambda and delta, to see if we can make an inference on short-run Granger causality between y and x in particular. And of course, a traditional disturbance term is this guy right here, which I need to make sure is white noise. So in comparison with the error correction model, we find here that in the ARDL model, the ZT minus 1, which is the lagged error correction term in the error correction model, is replaced with these lagged values of dependent and explanatory variables. And so you notice, as I indicate here, that if you replace the long run components, which is this term right here, with the lagged residuals are extracted from running this long run model, as I show here, if we lag these residuals, then the model would revert to the error correction model, which is this guy here. And so what we do in the ARDL model is include the same lagged levels in the error correction model, but without restricting their coefficients. As such, ARDL model may be viewed as a form of unrestricted error correction model, as some have indicated, because all the long-run relationship variables are clearly, completely specified. They are not restricted.